In this video, we present Olympia, a Solidity fuzzer benchmarking tool. Solidity is a programming language for writing smart contracts deployed on the Ethereum blockchain. In recent years, many different fuzzers have been developed for finding bugs in Solidity software. We are interested to see which of these fuzzers are the most effective at finding vulnerabilities in our software. Fuzzer is a C benchmarking tool which generates mazes and then translates them to buggy programs. We create Olympia by taking these mazes generated from Fuzzer and translating them to Solidity code. On the left, you can see a simple maze with only 4 cells, where the entry point of the maze is cell 0 and the exit of the maze is cell 3. There is a path to the exit simply by traveling through cell 1 on the right. On the right, you can see the corresponding Solidity code. Intuitively, the fuzzer will act as an agent traveling through the maze. We translate each of the maze's cells to a function. For example, you can see here we have functions 0 and 3 corresponding to cells 0 and 3 respectively. We omit the definitions for functions 1 and 2 for conciseness. The fuzzer can then traverse the maze by calling the functions corresponding to the cells. Inside the function bodies, if some conditional is met, the next cell value, which stores which cell the fuzzer can travel to next, is set to the corresponding value. For example, here if you look at cell 0, we translate this to function 0 and we can travel either to cell 1 or cell 2, depending on whether the if or the else if conditions are met. But there is a problem, since fuzzers are able to call arbitrary functions in a contract in Solidity in any order. Thus, we need to ensure that we always only call the function corresponding to the current position of the fuzzer in the maze. Therefore, we decided to make all of the functions corresponding to cells internal and define a single entry point to the maze contract. We define the step function, which can be seen here on the right. The step function takes the input from the fuzzer and, corresponding to which value the next cell variable is set, calls the correct function corresponding to the fuzzer's position in the maze. So, in the first call to the contract, next cell will be initialized to 0. Therefore, function 0 would be called first by the step function. For technical challenges we faced during the development of this translation, refer to our paper. Our results show that the Solidity fuzzers perform very differently, with ITY-fuzz finding the most bugs for all maze sizes. Here you can also see the results in a cactus plot, where you can see how many bugs each of the fuzzers was able to find, and also how long it took to find these bugs. We can see that ITY-fuzz strongly outperformed all other fuzzers in terms of runtime as well. Lastly, we show a Venn diagram of the specific instances each of the fuzzers was able to solve. Here we see that there were no instances ITY-fuzz wasn't able to solve that another fuzzer did solve. You can find our codebase for Olympia via the URL on the screen.